6, we're going to look at the atomic structure of an atom. But before we get to that particular concept, what we need to do is look at a particular thing called light. And light is essentially the visible part of a vast spectrum of electromagnetic waves. And the electromagnetic spectrum that you see here, shown towards the bottom of the screen, is an entire spectrum of radiation that is present in our world, from visible light that you see as this very small subset in this spectrum, all the way to gamma rays and down to radio waves. And the electromagnetic spectrum has different wavelengths, which then have different frequencies and energy values associated with that. But how did we actually figure this out? So it turns out that there was a scientist named James Clerk Maxwell, and he was the one in the kind of mid to late 1800s that described the electromagnetic radiation as such, in that light is actually made up of two components, an electric field and a magnetic field that travel in one direction. And these are made up of waves that coalesce together to give you that particular wavelength of EM radiation. And it turns out that we can use specific terminologies to describe light in a more general sense. So if we take an XY axis shown here and we put a wave like so, there are essentially three things that you're going to need to be able to describe. One is the wavelength. And wavelength, most of the time we use a symbol to describe or denote the wavelength, and this is the Greek symbol lambda. And the wavelength is described as the crest on one wave to the crest of another wave, right adjacent to it. And that length, measured in distance, is the deciding wavelength of that particular light wave. The frequency is described as the amount of time for a particular wavelength to actually go from one crest to the other. And we denote that as the Greek symbol nu, and it looks kind of like a little V with a little tail on both ends. And it is in units of time. More often than not, it's in the unit of per seconds. Now, per seconds, we can write it that way, or it can be written, I have seen it written as second to the exponent minus 1. But either way, they mean the same thing, but I will say that more often than not, a lot of times frequencies of waves are referred to as hertz, or Hz for short. So hertz is the exact same unit as 1/seconds or seconds to the minus 1 power. They all are a particular unit of frequency. Now keep in mind, frequency is a unit of time, so it is possible to see other time units other than seconds, like minutes or hours, that could be utilized, although I will say more often than not, in our chemistry realm, it is usually in seconds or hertz. And then the last thing that you might see about a light wave or any kind of wave in this particular class is amplitude. And amplitude is going to be the value of how high a particular wavelength goes beyond the x-axis. And so that tells you essentially the intensity or the amplitude, if you will, of a particular wavelength of light. We're going to be looking at how wavelength and frequency are related to one another, and we won't spend a whole lot of time with amplitude. But with that being said, let's talk about just frequency and wavelength. So it turns out if you take the product of frequency and wavelength, they actually multiply together to produce a specific constant value when this is in a vacuum. And this value we write as a lowercase c, and it is the speed of light. And that constant value ends up being this. So I would definitely put this in your toolbox of constants to remember. And it's 2.99 times 10 to the 8th meters per second. So that distance that is utilized in wavelength is meters when it comes to looking at the value, the constant value for the speed of light. Now, when we're talking about light, there is another aspect of it that I want you to be able to understand, and this is this thing called interference patterns. And interference patterns, the way they work is if you happen to have, say, two wavelengths of EM radiation or light, say we have this sine wave here and this sine wave here. If these two sine waves come in contact with one another, they're going to interfere in some way. And if they're exactly the same sine wave, same wavelength, what they're going to do is come together and become a constructive interference pattern. And this will look something like this. It'll be a bigger amplitude to that sine wave. However, if you happen to have a sine wave and another wave that has the same wavelength but is considered a cosine wave, then they come together. They will interfere because their amplitudes are opposite of one another. What happens is their wave, when they become interfered with one another, they become a destructive interference pattern. And their wave will look something like this. It'll be just straight. It turns out that understanding these interference patterns is pretty important when it comes to understanding how light behaves overall. And where this became very evident was through an experiment that was called the double slit experiment. And the double slit experiment works kind of like this. You have a light source, a particular distance from a barrier. And it turns out, in this particular image, we're going to use a metal sheet as our barrier. And in the barrier, there happens to be two slits or two holes. You'll see one that's right here and one that's right here. That is of a distance that is approximately a very short distance, sometimes a wavelength apart from one another. And what happens is when that light source passes and hits that barrier, it'll actually pass through each one of those slits, and they act like as if they're now two different sources of light. And if light is traveling as a wave, they will come in contact with one another and interfere in either a constructive or destructive interference pattern. And what you will see as the light actually hits a screen is something that looks like this. You'll see constructive light patterns here, and it will look like lines on the screen. And then in between those, you will see what look like destructive, where you see no light in between each one of those constructive interference patterns. And this particular experiment is very important This was done by several scientists back in the early, mid to late 1800s, that showed that, hey, light acts like a wave, which was really important because we had some conflicting information as to whether light acted as a wave or in some other pattern. And it turns out what was really neat is that we could actually translate that not just from using light, but to electrons. And we could actually show that the same interference patterns show up when electrons are used to shoot towards a double beam or double slit barrier. You get the same interference patterns of constructive and destructive patterns. So that we were like, okay, so electrons that make up the atom itself, help make that structure, act like waves. And so that was really, really important information. And what we figured out was, what does this tell us? Hey, light and electrons behave really similarly, and electrons behave like a wave. At this point in time, this was in the late 1800s, our thoughts and our thinking of how parts of the atom starts to behave and work. And this would help allow us to start to build the atom together physically. Unfortunately, there were a few things that broke down this thought of electrons acting as waves, and light also in that story. So it turns out that there were two paradoxes. One was called the black body radiation paradox, and the other one was the photoelectric effect paradox, where it turns out both of these issues, which I will discuss each one in later videos, broke down the idea that light and electrons behaved as a wave. And so at this point, I'm going to not talk about the bulk of black body radiation and photoelectric effect. Watch the next videos about each one of those to further our discussion on the atomic theory of how the atom is put together. But for right now, what I want us to do is let's stop and let's take a look at the light working as a wave and using equations to describe those waves in some example problems. So let's move to example problem number 1. And this example problem states that what is the frequency of, let me move to the right pen color. What is the frequency of green light that oxygen atoms emit in the aurora borealis? And it says the light's wavelength is 557.7 nanometers. I want to point out to you guys that a lot of times when visible light, and so we know it's visible because we use the word green, so we can actually physically see it with our eyes, is a lot of times written in the units of nanometers rather than just meters. So please pay attention to that when doing your example problems. So when it comes to this particular problem, we're talking about the word frequency and wavelength, and we've seen an equation that will help us describe a relationship between those two, and it's this one. The speed of light equals the wavelength times the frequency. And so this question says, what is the frequency? So what we're going to be solving for is nu. And so let's rearrange this equation to be solved for nu, and that makes it a little bit easier for us to solve this problem. And so we are given wavelength and the speed of light, c, is our constant, so we can just plug these numbers in. So 2.99 times 10 to the 8th meters per second is the constant for speed of light. And the wavelength given to us, remember, is in nanometers. But since the speed of light is in meters, we need to convert nanometers to meters. And a very quick trick to do this is take the number that's given to you and put that into scientific notation where you put it times 10 to the minus 9. And so I'm just going to, and that's a very, very quick trick to convert from nanometers to meters. So it looks something like this. 557.7 times 10 to the minus 9, and this would be meters now. So if you just add that times 10 to the minus 9, it goes from nanometers to meters automatically, and you just leave the number as is, and that's okay for this particular problem. We'll plug this into our calculator and round it to the appropriate number sig figs, which is 3. The speed of light is an experimental calculated number, so it's a measured number, so its significant digits matter. And I get 5.36 times 10 to the 14th per seconds, because meters cancel out. You could write that as 1 over seconds, or seconds to the minus 1, or hertz. Any of those three will be perfectly sufficient. So that is our answer for example problem number 1. For example problem number 2, this states one of the frequencies used to transmit and receive cellular telephone signals in the U.S. Hold on just one second. Okay, try that one more time. One of the frequencies used to transmit and receive cellular telephone signals in the U.S. is 850 megahertz. What is the wavelength in meters of these radio waves? So again, we're going to be using the word frequency and wavelength. So we know that the equation that we're using is the speed of light equals wavelength times frequency. So let's rearrange this problem to solve for wavelength. And that looks like C over frequency. And we'll plug in our values. We know the speed of light is 2.99 times 10 to the 8th meters per second. But our frequency is kind of in a weird unit. It's megahertz. So we know hertz is the per seconds. This must mean megaseconds. So we need to convert mega back to just regular seconds. And just a really quick way for you to do this is use the base unit as seconds. And then if you go deca, hecto, kilo, the next one is mega. And so we count how many times it takes us to move over to that location. This will tell us how many times we need to multiply or move our decimal. So that's 1, 2, 3. Anytime you move above kilo, you're moving every prefix, it's 3 more. So we've gone 1, 2, 3, and now this will be 6. So this is times 10 to the 6th that we will add to that value. So we'll put 850 times 10 to the 6th per seconds. And that will get us out of megahertz into just regular hertz or per seconds. Our seconds will cancel out here, and this will just leave us with meters, and which is a unit of distance that our wavelength will need. And that's what our problem asked us for, was in meters, the wavelength in meters. So we'll put this in our calculator, we'll take our speed of light and divide it by our frequency, and I end up getting to 3 significant digits, 0.352 meters. So this is how you use the equation of speed of light equals wavelength times frequency in a couple different problems. And if you have any questions, don't hesitate to contact me through email or through comments on YouTube. I'll see you in the next two videos about the blackbody radiation and photoelectric effect.